Okay, so thank you very much, Spyros. Feel free to start whenever you're ready.
Okay, good. Thank you very much for the invitation, Elias. I'm grateful for this. It's great to actually be able to present my research to your group. As Elias said, so I'll be talking about interdependent infrastructure, basically, and how we can kind of manage resilience in the face of pandemics and climate change, the specific kind of threats that I've looked at so far. So first of all, just a few words about me. So this is me, young and happy. So basically, I've got some experience with smart grids and renewable energy, and recently I started kind of shifting towards infrastructure resilience in general the last few years. So I've worked on projects related to multi-agent systems, multiple energy carriers, reliability, and so on. And recently we got a small project on using graph theory for interdependent critical infrastructure networks. I'm not going to talk a lot about that because it's we haven't yet started, but I'll talk about the underpinning concepts that we used to kind of develop this proposal. And so basically my research is kind of split into several themes. Now it's centered around critical infrastructure resilience. And obviously multiple energy carriers contribute to that, as we'll discuss later. And it's all about reliability and resilience, essentially. And I'm also going to mention how I use the concept of agent-based or intelligent controllers to kind of contribute into the whole, obviously, beyond the smart grid, into the resilience aspects. And I'll talk about the interdependencies and climate and pandemic threats as well. So that's kind of shall I say, the summary of my research. Yeah, basically I mentioned the overview of my presentation already, but it's I'll start with the concept of resource aggregation, which I'm sure most of you are familiar with. So I'll just kind of run through those just to make sure everyone is on the same page. And I'll discuss optimization of multiple energy carriers, specifically because that's what we did in a couple of projects, and focusing especially on thermal, electrical and thermal energy storage, which we did in an Innovate UK project, more practical application. Then I'll move on to reliability and resilience, and then discuss what we mean by interdependencies within kind of infrastructure networks. Then I'll talk about pandemic and climate resilience. Starting with the concept of virtual power plants, I'm sure all of you are aware that they are basically an aggregation of energy resources. It could be micro generations like this example, or electric vehicles, or multiple sources, small and large. I mostly focused on micro, basically distributed energy resources. So they operate as one entity. We could have several layers of aggregation. In the past, I've considered the microgrids to be one layer below the virtual power plants, but it's basically kind of an open up architecture, as you may be aware of. Yeah, in this example, we used electric vehicles as the resource to be aggregated. Yeah. Now, moving on to what we mean by multi-agent systems. I'm not sure how many of you have come across the concept. It's basically an autonomous piece of software that is it is an extension of the object-oriented programming And the agent is basically acting semi-autonomously, or mostly autonomously, based on the inputs from its environment and communication with other agents and so on. So this is a basic architecture. There are multiple variants, of course, but this is kind of a more standardized approach, where you have the agent and you have some directory facilitators and another kind of ancillary processes, including a message transport system, which is used to communicate between the different agents. And the agent will take a decision, will communicate to other software or hardware, depending on the application. In the environment of distributed energy resources, we have obviously also hardware, control hardware that is more low level and is acting to control the resource. So this will interact with the agent high level functions to actually control the system. And between them, the agents will communicate in a way that facilitates the aggregation and communication between the agents, of course, and coordination, sorry, between the agents. Yeah, we also worked on an IEEE standard, 2660.1, which actually defines more specifically the architectures that apply to kind of industrial agents, as we call them. Sort of, it's because obviously agents are a computer science concept. Industrial agents involve more than just kind of code. They involve hardware. So we have several kind of categories of how we actually how the agents interact with the hardware. It could be that the agent is located within the same controller, or it could be a different controller, or it could be just somewhere in the cloud, and then it communicates with low-level control hardware, and so on. So these are just different architectures. Now, this is a multi-agent system that I've developed a long time ago, and basically the concept is that we have an agent controlling a generator or a DER in general, a resource, and these communicate between them or the aggregator, and we have obviously different layers. And at the top we have the virtual power plant aggregator, which is acting as a single overarching kind of agent. So this is obviously a multi-agent system because it contains multiple agents. I mean, so far so good. This is a kind of a control approach, which I'm sure many of you are familiar with. Now, the thing is how we actually use this is it's a tool. It's nothing more than a tool. Now, I'm going to start kind of progressing to multiple energy carriers, which is one kind of aspect of interdependency between electricity and gas networks or other networks, which is obviously the obvious one, the more kind of obvious interaction between infrastructure networks. So the concept of energy hubs, in case you haven't come across it, it's basically a point in the networks where we have multiple inputs and multiple outputs in terms of energy. So we have energy carriers like electricity, natural gas, and so on coming in. Then there are conversions happening. Obviously, we have a gas turbine or a turbine generator consuming gas, producing electricity and heat, if it's a combined heat and power device. And we have possibly district heat actually feeding into this heat as well, and electricity feeding into combining the electricity inputs there. And we might have a battery or thermal storage, and of course the output is going to the loads. Again, we have possibly different, some of the same energy carriers. Now, this is the conceptual view. In terms of, so it's basically an integrated approach for optimizing multiple energy carrier systems. And it's defined as a unit where multiple energy carriers can be converted, conditioned, and stored. Yeah, so there are different conversion devices and so on that are used for storage devices. It's not a new concept, it's a fairly old concept. More recently, I tried to use this with multi-agent systems. But before I go into that, I'll just mention that there is, if we want to actually optimize multiple energy carriers, we need to sort of couple them in some way and come up with an objective function. I mean, since this is the optimization group, you all know about objective functions. So the basis for the objective function in this case is the coupling matrix, which is linking the outputs to the inputs, or the inputs to the outputs, depending on which way you look at it. So it's a simple matrix multiplication. You have well, let's look at this one, the outputs on one side and the inputs on the other side. So the outputs are kind of fed into or multiplied with the coupling matrix, which contains some parameters here, and you get the expected outputs based on that. So these parameters, the linking factors are defined by the structure of the energy hub. So, for example, in this case, we have the natural gas going into a CHP, and this is converted to electricity and heat. So in this case, we have a parameter here representing the CHP system, which will, and this will represent the amount of natural gas energy that goes, or power that goes into the electricity kind of outputs and the gas output as well. So that's the role of the coupling matrix. Now, I did mention that I used multi-agent systems in this concept. Essentially, it's a kind of an adaptation of the classic sort of aggregation system. So where you have commercial and technical aggregators, you have also the hub agents, and the hub agents act as a second layer of aggregation below the virtual power plant sort of aggregation layer. And within the hub, you have the different resources, which are controlled by the individual agents. And this could be, the resources could be a CHP, an inverter, or a reformer, or a battery, or whatever, things to convert or store energy. So that's a kind of the generic approach. Now, I won't dwell too much on that. I mean, technical aggregator is basically the aggregator that is sort of looking after the network performance, things like voltage level and so on. Whereas the commercial aggregator deals with the markets, the costs and so on. So that's kind of again a fairly established approach. Now, the way optimization happens in this case is that the hub agent first of all kind of discovers what kind of resources are under the hub. Then it requests it populates the matrices with efficiencies, types of inputs and outputs, and ratings for the devices. so that it knows what's going on, and then it has enough information to construct the coupling matrix. So these are the initial steps. Then we start the iterative process of kind of optimizing, obviously with time steps. So I don't know, maybe 5-minute or half an hour time steps. So we start the optimization. It optimizes the matrix. I'll talk about it optimizes this matrix. I'll talk about the objective function in a moment. And then it basically sends the optimal matrix to the aggregators, and this is essentially an approval sort of process. And the aggregators are able to request a modification if they judge that this optimal position kind of conflicts with either market operation, or more importantly, possibly a technical operation. If it causes a voltage violation, voltage limit violation, then it's not good. So then we came up with a process to kind of implement this modification, because obviously when you modify an optimized position, then it's no longer optimal. But of course we have constraints, so it's a kind of a sort of a way to kind of work around the constraints without having to re-optimize, and especially because those constraints are not within the objective function, they are provided by an external entity. So technically, it's quite difficult to include them into the optimizer. So the approaches we considered are first of all to modify the demands. Simplest one, if we can do that. If not, optimize the dispatch factors, so the factors within the coupling matrix. So if we can, for example, shift a little bit of gas into heat production rather than electricity, then that might be kind of that might solve the issue. Or as a last result, before sort of taking radical measures like rejecting the modification, final action would be to trade with other agents. So and that's where the multi-agent system kind of mostly kind of provides a benefit, because that's where we can kind of have coordination between energy hubs for the benefit of the whole virtual power plant. So then, yeah, the final bit is then that the hub sends the final dispatch factors to the individual agents to implement the position, the optimal position, and the final matrix to the aggregators. Now, this is a kind of a mapping of the interaction. So basically, this is the initial setup. We kind of we have the registering of the agents to see what's going on. We do forecasts, which are necessary for the next time step, obviously. Then we calculate the energy hub optimality in each of the hubs. Then we communicate. Then the hubs communicate with the aggregators. Then if the aggregators find a mismatch, then they request a modification, and then we iterate through the methods of modifying the optimal position. And if methods 1 and 2 don't work, then we start trading between the hub agents. And then we implement the final position. Now, this is the overall kind of objective function. So it's based on the sum of utilities for each agent. So we optimize the utility of the agent, which is essentially at the end of the day dependent on the aim of the virtual power plant. Is it to optimize costs or emissions, or do something else, possibly resilience or reliability? I'm going to talk a bit more about that later on. So it's to maximize the utility, or in other words, minimize the cost. So it's a cost function essentially. And it's a sum of the individual hubs that we consider here. So we've done a simple case study with basically one hub that's the kind of a standard microgrid essentially, and it's the main component here is the CHP, which converts natural gas to electricity in heat. And we found that if we do the optimization as compared to a kind of non-optimized approach, then we saved about 6% of costs and 14% of emissions. That's kind of a simple demonstration of the concept. And now, one kind of benefit of that is that we might not need to go to the balancing market if we have this kind of aggregation system. So and that's essentially it's considered at the point where you might get a mismatch, or you might get a request by the aggregator to modify the optimal position. So by trading between the energy hubs, we avoid the balancing market, and this results in reduced costs basically. So we manage it within the virtual power plant instead of getting external, going to external trading. So we tried to kind of implement this in a real system. So we partnered with Moixa technology, which operated an aggregation system, and with Daram and Sanand. Sanand is they produce thermal batteries, and we sort of came up with a sort of a trial where we used the batteries provided by Moixa, and the electrical batteries by Moixa and thermal batteries by Sanand, and excuse me. And we made the controllers. We actually used a Raspberry Pi in this case, but we essentially used the aggregating solution that Moixa provided in that case, and we sort of tested the concept. So this trial was using storage, electrical storage and thermal storage, and we had an optimal control implementation on a Raspberry Pi to optimize those two. And there is a kind of a facility of actually communicating with other Raspberry Pis, obviously, but we haven't implemented this in this trial. We just but we did kind of develop an optimal control methodology based on Hamilton-Jacobi-Bellman equations. So we use that. It is a very robust optimization methodology that was used. So it's mapping the whole state space, and it's pre-computed. So then when you try to implement it to real-time control, it's basically just a lookup table. So it's very fast. And yeah, so we use this this approach to optimize electrical and thermal storage within a simulated household in a way. And yeah, so basically we had the researcher actually trying to switch on and switch off a few loads to see if the to try to kind of deviate from the forecast and make sure that the optimal solution, the optimizer, actually is able to sort of follow and adapt to changes in the load, which, as you probably understand, are semi-random, I should say. So yeah, we actually found that the system is able to kind of keep up, essentially, which is good. So now, so far we have discussed concepts that we are probably all more or less familiar with, so smart grids and distributed energy resources. They're kind of widely researched. Now, I'll kind of move on into the resilience. Obviously, this is a kind of an animation of a cascading failure. Within this is a computer network, but it's essentially the same concept. Yeah, so a few failures could actually cause a wide system collapse if the conditions are right. So we should make sure basically that the conditions are not met for a cascading failure, for a failure to initiate a cascade. And just to kind of bring everyone on the same page with reliability, it's kind of divided into security and adequacy, where obviously security is the ability of the system to kind of provide to kind of deliver the energy, whereas adequacy is about having this energy in the first place to be able to be delivered. The indices that are widely used are obviously customer minutes lost, or SAIFI, the system average interruption frequency and duration indices, or customer-based, and so on. So these are obviously well developed for electricity networks, but having talked to other infrastructure, to researchers from sort of other infrastructure networks, it's not clear. I mean, they call them in a different way. The concepts are similar, but I don't think there is I haven't found a kind of a unified sort of approach that can be implemented or followed by all infrastructures, like beyond energy, beyond electricity and gas, for example, water or telecommunications and so on. So although there was a kind of I had some discussions, and it seemed that the duration of an interruption kind of provides a good indication of the restoration capacity of any kind of infrastructure system, whether it is electricity or gas or water. But anyway, I mean, that's open to debate, I guess. In terms of resilience, so that's reliability. How we go from reliability to resilience depends again on the approach. In a CIGRE working group I've been participating, we kind of defined resilience in power systems, at least, as the ability to limit the extent, severity, and duration of system degradation following an extreme event. And of course, we divided this into key actionable measures like anticipation, preparation, absorption, adaptation, recovery, and sustainment of critical operations. So And of course, then we kind of adapt after the event. I'm sure many of you are familiar with a trapezoid, the resilience trapezoid, which is essentially the development of of resilience across an extreme event. So we have the pre-disturbance kind of phases where we try to increase resilience in anticipation of an extreme event. Then when the event happens, resilience starts to drop. We sort of try to absorb sort of the event as much as we can. And then we just try to maintain at least the critical system operations, and then restore the system, recover to normal, or at least close to normal operation, and then we learn from it and try to increase resilience further. So this is the approach that we took in that working group. Now, these are just basic concepts. We considered kind of resilience metrics. So how do we actually measure resilience? But that's still a work in progress, I should say. There is quite a bit of research on that out there if you want to kind of find out, obviously. Now, we also considered the interdependencies, and that's kind of one of the key concepts in this discussion, in this presentation. So different infrastructure networks have different equipment, and obviously these equipment depend on each other. So, for example, a substation will depend on telecommunications. We need to kind of have remote access to some of the substation data, acquisition, and so on. And the same for gas and possibly water installations as well. And generators obviously need gas, so they depend on compressors to actually deliver that gas, or other gas infrastructure equipment. So the interdependencies are rather complex, and of course, if a substation fails, then local pumps for water have to go out. Local compressors for gas go out. Switches for telecommunications, like or mobile mobile network masts, go out, and so on. So if there is a cascade, it could cascade beyond the electricity network. So it could cascade to different infrastructure. And then it's the question of when there is a disaster, for example, an earthquake, and multiple utilities are cut off, which one do you start first? Obviously, you need gas to start up gas turbines. You need electricity to start pumps. So, where do you start? It's a kind of a catch-22 situation. So we sort of looked at the kind of conceptual approach of interdependencies, and there's different approaches in the literature. There are physical, geographic, cyber dependencies, and so on. It's a sort of complex array of dependencies between those infrastructures. But then the question is, how do you actually consider resilience or reliability into a more kind of organized manner? Because if you look at the metrics that the utilities use, power and gas have largely similar metrics, what I already mentioned about reliability, like expected energy not supplied, and so on. Water networks have the event risk index or other kind of metrics of their own. Telecoms consider dropped packets as an index. Transport, like cancellations and so on. These are largely kind of different they measure different things, but they're not that different if you look at them on the high level. So the idea is to kind of transition into a more kind of integrated approach where we have metrics that can kind of cover or at least interact with multiple critical infrastructure utilities. And if you look at actually what happens during a disturbance or during an extreme event or previous to that event, most of the infrastructure utilities, they basically do the same thing. They model the scenarios, the threats. During the disturbance, they again do similar things. Like in electricity, we do fast frequency response. In gas, they use the line pack as a storage kind of deployment. In water, they do rezoning and water injection. It's kind of again resource oriented and so on. Yeah, and in the restoration, again, they're doing similar things, and post-restoration, obviously, they all do some learning. So if you look at it, it's not that different. So so we could kind of work into kind of extending the concept that we already have in the electricity networks to other infrastructures. Now, I did mention pandemics and climate change. Starting with pandemics, we consider in this kind of at least in this kind of work that we did, we considered people as part of the network, because essentially epidemics spread in a way that is that it can be modeled as a network. Okay, networks are defined as obviously infrastructure networks, but they can also be defined as biological networks and so on. I mean, the fundamental concept of network is the same. So we considered people of different levels, like, I don't know, director, manager, CEO, and so on, down to operators as nodes within a network, and they are linked by their interaction. So when they talk to each other, they have an interaction, they might transmit disease between them. And eventually, if an operator goes off sick, then this sort of disruption caused by a disease can spread into actual assets, not obviously as an illness, but maybe if there's a fault and the operator is absent, then no one can clear that fault, so it cascades. So that's the idea, and so we consider sort of the individuals as you could call them agents, but we haven't got into that point yet. But at least nodes that have certain characteristics: location, susceptibility, and if they are linked to an asset or not. Obviously, directors and high-level staff are not linked to assets, but then you have.
Okay, if I'm the one, okay.
So
excuse me, sorry, excuse me. Can everyone not talk?
I will send it to you.
Adedayo, sorry. Can you hear me?
One is available.
Sorry, Adedayo. Can you hear me? Can everyone please mute if they are not talking? Okay, Spyros, okay, please go on.
Okay, no problem.
Okay, right. So yeah, so basically local managers and operators can actually be linked to certain assets, and if they're infected and there's a fault, the fault can remain ongoing and could cascade to other assets. But if we have if we take measures to actually isolate or split the locations of those operators, and they are able to kind of operate the same assets, then if one of them is infected, then we have the other one as a backup. Kind of common sense, really. But then we secure a fault in a in one asset that doesn't then cascade. So that's the simple approach. So we kind of played with a toy network. So we kind of made up a sort of utility where we have the big manager like CEOs and so on. We have the technical staff, which are basically mostly office-based, like planning for planning and so on, and the control center staff, which are critical to controlling the network, and obviously the maintenance and operations staff, which are in the field. And we considered two main interventions. One is to split the control center into two, having a backup control center. And the other one is to, obviously, whoever doesn't need to be on site, they should be working from home, which are two obvious measures that were taken during the COVID pandemic. And we looked at the impact of that. We looked at we considered graph theory. We looked at the characteristics of the network, something called closeness centrality, which measures essentially the links between nodes. The distance, it's sort of equivalent to the distance between one node and another node throughout the network. So all the combinations of nodes, considering all the combinations of nodes. And as we can see from this graph, the most critical kind of nodes are basically the CEO and some kind of big managers which are in contact with a lot of people. So if we actually let those people work from home, we kind of eliminate this central kind of hub of activity where a virus can propagate through, and we end up with a much more much less kind of interactive graph. So so these nodes are basically not interacting with any other nodes, and these are essentially the office-based staff that are working from home now, and even the field staff, maintenance staff, they have much less connectivity with other people. So even if a virus kind of gets into the company in one place, maybe it doesn't propagate that easily to other sites. And that's the idea, kind of, to prevent kind of propagation. Of course, we consider assets as well, because we, as engineers, we care more about our precious equipment than people. But well, that's not true. But anyway, so considering assets and how these might be influenced by or affected by a virus, we found that these two interventions, splitting the control center and working from home, could actually reduce the risk by about 26, or the sort of the connectivity, which is sort of linked to the risk, obviously, by 26%, which is non-negligible, I would say. So, so this is sort of a preliminary study and a preliminary approach of considering how pandemics could influence, could affect the resilience of a power system. And this could also translate to other infrastructure systems as well, through the interdependencies that I've discussed previously. And the last bit is about climate. So again, this is a sort of preliminary study we've done in a hackathon that I participated in. We considered some reliability indices And we've seen, we considered also some wind drought events where basically it's a climate change kind of scenario that the Met Office sort of modeled. And we considered different extremes, one in 20 years, one in 50 years, one in 100 years, and a very extreme event of wind drought. And we've seen how these might affect these reliability indices. And we've seen that there is a sort of correlation between the severity of the event and the impact in terms of reliability. So that's a very simplistic approach. Obviously, we need a much more detailed model to kind of get more insights. And finally, yeah. So while we're on climate, so just to mention what we're doing in the climate adaptation working group of SuperGen. The first thing we've done so far is to submit a response to the call for evidence to Parliament from the Joint Committee on the National Security Strategy, where they considered climate adaptation. And we said that there's currently no established and commonly accepted definition for resilience across different critical national infrastructure systems. And that's important. We said that regulators can play a role in actually linking those industries. And we considered that it might not be sufficient to consider a single event resilience definition, because obviously we might have multiple events happening at the same time, like storms, floods, and so on. We should make use of the adaptation reporting power, and policymakers should manage the long-term risks and so on, and use policies that we already have more effectively, and try to be proactive instead of reactive. And finally, that we should involve the Met Office and organizations that do climate modeling to actually inform the infrastructure adaptation strategies. And what we're trying to do now, before the working group kind of wraps up, is to come up with a stress test definition for a stress test across the infrastructures to include sort of climate modeling, so as a more or less a technical and policy recommendation to see what can be done about that. Sorry, and so yeah, that's the working group. And yeah, just a quick note on what we can do in terms of improving resilience. Obviously, we have the tools to manage things like network reconfiguration within smart grids, so we could use that to improve resilience. And we could use distributed energy resources to improve the performance both before, after, and during the events. And using control of distributed energy resources as a tool in that respect. And just to clarify that, obviously, these control technologies, they can cross the barriers of infrastructure. It's not there. They can be applied not just in electricity, but in multiple energy infrastructures beyond electricity and gas and so on. So that's it from me. Thank you very much.
Thank you very much, Spyros. That was very interesting, and I think there is a lot of useful information in there. I mean, your presentation was very detailed. A lot of, you were very descriptive methods, and a lot of new stuff like organization of resilience indices across vectors, climate, everything was there. So I think we have time for 2-3 questions, and anything else can be discussed with Spyros. I mean, feel free to contact Spyros if you want. Do we have any questions? I'm stopping recording, by the way.
Hi, guys.